Okay, we are just going to be looking at what a stoichiometric conversion is, basic stoic calculations. Pretty simple. The whole concept of stoichiometry is essentially, or it can be pictured this way, just converting the amount of one substance, one reactant or product or whatever, into an amount of the other. And what's missing from this diagram is the central point to all of these, which is the mole ratio. Uh, and so the mole ratio is what allows us to convert an amount of A into an amount of B. Obviously, then we need to have moles of A, and which can the mole ratio then convert into moles of B. Now, the mole ratio itself comes from the balanced equation. We'll get to that in just a second. Getting moles of A or B, though, that's going to involve some kind of mole conversion, which we've probably already done at this point, or we have already done at this point. So converting 2 moles of A, well, you could start with any number of different amounts of A. You could have a mass of A and then convert it to moles, or a volume of A, if it's a gas, let's say, and convert it to moles there. Or you could have a volume of a solution of A and then convert to moles there. And the way we do those, we've already covered, but to convert from mass to moles, we divide by the molecular mass. To go from volume of a gas at STP to moles of A, we divide by 22.4. And to go from volume of a solution, well, if you have volume, you need to multiply volume volume times concentration. N is equal to C times V, and that'll get you moles of A. And then by multiplying by a mole ratio, just like any other conversion factor, that'll get you into moles of B. And then you can do the same thing. You can go to mass of B or any of the other ones, volume of a gas or volume of a solution. Okay, and those are all things that we've done before. So only the new part then is this mole ratio. Everything else is just a mole conversion. Okay, so I said that the mole ratio came from a balanced equation. Let me show you what I'm talking about here. Here is a balanced equation, and if I knew, for example, that I had 0.4 moles of nitrogen gas, because the mole ratio between nitrogen and hydrogen, it's a 3-to-1 ratio. And so if I had 0.4 moles of nitrogen, I would need 1.2 moles of hydrogen. And so this works like any other conversion factor where my units cancel out like that. So I would have moles of hydrogen. Likewise, if I wanted to convert moles of nitrogen into moles of ammonia, I would have to use the mole conversion between nitrogen and ammonia, and that's a 2-to-1 ratio, 2 moles of ammonia for every 1 mole of nitrogen. So in other words, 0.8 moles of ammonia can be produced from 0.4 moles of nitrogen. So the central point to this, or the central concept, is this mole ratio, but we can tack on stuff on either side, like for example mole conversion. So say if I told you that I had 15.0 liters of hydrogen gas at STP, and I wanted to know how many grams of ammonia that would produce, assuming I had enough nitrogen to go along with it. Well, just like all our other mole conversions, we always start with what we've been given, which is volume of a gas. I need to convert that to moles, and then convert moles of hydrogen to moles of ammonia, and finally convert moles of ammonia to mass of ammonia. So a lengthy conversion, but if we just keep in mind all the parts that we know already, like converting volume of H2 to moles of H2 at STP, I'm just going to divide by 22.4. To convert moles of hydrogen into moles of NH3, that's where the mole ratio comes in. And then to convert moles of ammonia to mass of ammonia, I just multiply by the molecular mass. So again, the only new thing is this mole ratio, which comes from the balanced equation. And so we go along and we're going to do our calculations. So divide by 22.4 liters per mole, multiply by the mole ratio. Here's the important part. I want to put ammonia on top because that's the one I'm going to, and I want to put the hydrogen on the bottom because that's the one I want to get rid of. The hydrogen cancels out there and there. If you think of it as a unit like that, just like liters cancels out there and there. Currently, I have moles of ammonia, and when I multiply by the molecular mass, let's call it 17.0 grams per mole. Now the moles cancel out, and I'm just left with grams of ammonia, which gets me 7.59 grams of NH3. Okay, and so that's the basics of it. Let me just put another one up here for you, see if you can try this one. Okay, so iron will react with oxygen to produce rust, Fe2O3, and if we react 11.5 grams of iron, what mass of Fe2O3 will be produced? This is the one I'd like you to try, so pause the video, I suggest, and go ahead and work out the answer. I'm going to start the solution in 3 seconds. Alright, so just like before, let's kind of map out our pathway here. So I'm starting with the mass of iron, and just like before, when in doubt, convert to moles. It's always going to be our first step, almost always. And then once I have moles of iron, then I'm going to use the mole ratio to find the moles of Fe2O3. And then the last thing I'm going to do is find the mass of Fe2O3. And I'm going to do that using the molecular mass. So those are my steps. Divide by the molecular mass of iron, then multiply by the mole ratio, and then multiply by the molecular mass of Fe2O3. Here's what the calculation looks like. So 11.5 grams divided by 55.8 grams per mole. Once you balance the chemical equation, you can get your mole ratio for moles of Fe2O3 to moles of iron, and you see that it is 2 Fe2O3 to 4 Fe. You could reduce that down to 1 over 2. It's the same thing. But not necessary to get the correct answer. And then that's going to now I'm going to multiply by my molecular mass of Fe2O3, which happens to be the molecular mass of copper sulfate, but just a coincidence. And if you just kind of pay attention to units here, grams cancels out there and there, moles cancels out there, and then Fe cancels out there and there. The only units left are grams of Fe2O3, and the calculation is 11.5 divided by 55.8 divided by 2, or times 2 over 4, same thing, multiply by 159.6, and there it is there. Fe2O3 is, 16.4 grams of Fe2O3 is produced. Okay? Now, besides figuring out how much product you're going to produce, you can also work out the amount of the other reactant that you need. And so I might ask you what volume in liters of oxygen is required at STP, so I'll assume 22.4 liters per mole, and you can work that out as well. So it's going to be the same structure, just different numbers thrown in there. Again, at the center of this is the mole ratio. Why don't you see if you can work that out? I'll show you the answer in 3 seconds. Okay, so again, start at the very beginning. It's a very good place to start, I hear. And this is what the equation looks like. I'll show it to you all at once. Okay, so 11.5 grams divided by 55.8 grams per mole. Grams cancels out. Times the mole ratio, 3 oxygens for every 4 irons. Irons cancel out. Times 22.4 liters per mole. Moles cancels out there and there. That leaves me with liters of oxygen. And the answer you get there then is 3.46 liters of oxygen. Okay. So that's about all I probably need to do for that one, but I'm going to show you one little shortcut that only works if you're dealing entirely with gases all at the same temperature and pressure. Let's go back to our ammonia example and imagine that we had a known volume of hydrogen and was trying to figure out the volume of NH3 that was being produced under STP conditions. So because these are all gases, and because they're all at STP, and even if they weren't, it doesn't really matter, the conversion for gases, the molar volume of a gas, is the same regardless of the gas. So let me just show you what the equation would look like here. Okay, so the equation would look like that, and you'll notice that first to convert to moles, I divide by 22.4, then I multiply by the mole ratio to get moles of ammonia, and then to convert to volume, I multiply by 22.4. Well, dividing by 22.4 and then multiplying by 22.4 cancel each other out. And so really, all I'm doing is just multiplying by the mole ratio. And so I can go 45 times 2 over 3, and that's my answer. But you have to know that only works when you're dealing with all gases, when you're going from volume of one gas to volume of another, and they're all at the same temperature and pressure. Other than that, you have to use the long method of doing it by converting to moles, using the mole ratio, and then converting to whatever your amount is going to be. Okay? So that's it for stoichiometric conversions. Next video is going to involve something called limiting reactant.